So now we're going to go into taking one of those forms of actuation and putting it to work, designing a torque tube actuator or a wire actuator spring. And what I have here is really in its simplest form. And if you're interested in more advanced form, I'll be more than happy to share that with you. Or if I don't have it, I will direct you to who can help you with that. Like if you would like to perform some finite element analysis on actuation, we have the tools for that. They are not in this package, but I can tell you where to go and do that. So let's start with this couple of slides. So now we're going to start designing an actuator, and you need to make sure you know how to create these diagrams in order to limit your design box. Okay, so if I go to the left-hand side, this should look familiar to you. Now I have a stress and I have a temperature. Before I showed you one line here. Let me bring my friend here, the pointer or the pen. I have one line. As I increase the load, my temperature shift higher, right? As I go up and up, it was here. And as I apply load, it goes up to here, and then so on and so forth. Well, that happens for the entire curve, not just the AF. So if I draw small here, at zero stress is over here. At higher stress, it's over here. It shifts that way, okay? So the entire curves shift up. So what I'm trying to say is you need to know how to map these lines, so when you operate your device is inside some red box. Let's say this is your design box. Okay, so these slopes exist for martensites finish and starts, and austenite start and finish. Okay, and the slopes we typically call them, again, Clausius-Clapeyron. That's what the C comes from, Clausius-Clapeyron relationship. How do I create these curves here? Okay. And here's that principle again, and what I sketched here, I have it on the right-hand side. You can see the curve here with this green triangle is down here. As I apply higher loads, 100 MPa, 2, 3, 500, you see where this austenite that was here, it's shifting, you know, going higher. Not just the austenite, but the entire curve or majority of the curve is shifting to higher temperatures. So how do I obtain this ones? I hope that it's clear how you obtain it. To obtain this actuation curves or these hysteresis curves, you apply a load, say 100 MPa, and a stress in this case. You hold that stress constant and you simply heat and cool. You record the strain. And then you go to higher stress, 200 MPa, you heat and cool, and you create this curve, and so on and so forth. And that's how you can draw this map. And that's what I have described here. I'm just going to show two of them now. Now, you create this box. Here's one way of looking at it as a function of strain. This is as a function of temperature. You create this sensitivity as you increase or decrease temperature. So at all times, you know where you are. If you're operating here, you know what the temperature is going to be. If you're down here, you know what the temperature is going to be as a function of stress. Well, now you know as a function, now you need to know what that stroke is going to do. So this is how you get that. Applied stress as a function of actuation strain, which could be your displacement, your twist, or whatever that might be. So here are those curves again, okay? I apply one load or one stress, I get this curve. I go to higher stress, I get that curve. So on and so on and so on, okay? Now I take these curves at the end in the room temperature or the coldest state, and I take this point right here, and I plot it here. And I take that point, and I plot it over here, and so on and so forth. And I create a relationship. And then I go to my other side in the hot state, and I take this point, and I plot it over here, that point, and I plot it over here, and I create a relationship. This is extremely important. This is what we call the load lines. You need to understand what loads is going to look like when you use this thing as an actuator. So now let me take this plot and blow it up over here to the left-hand side. The hot state condition is here. The cold state condition is here. Now let's say I gave you this actuator and you chose, let me see if I have that slide, yep, over here. And one of you wants to use a constant force, meaning I take a piece of wire and I dead load it with a constant weight. Okay. Constant weights. That weight happens to be 300 MPa in this case, and it's constant, right? What does this mean? It means as I heat and cool, I go hot, cold. This is the amount of available stroke I have. So this is my design box. Heat, cool, and so on. I go from 5% to 0% or close to that. This is my stroke available. Now, you don't want to get that full stroke. You want to put a dead stop, a bracket to stop it. And that's what this top example means. I'm going to limit my stroke. I want to go only from hot state here to partially. I don't want to keep going. Okay, I want to stop here. So I want to exercise my actuator to its 60% stroke, for example. Why would I want to do that in real applications? Any guess, anybody? Why want to limit my stroke? And give me the #1 reason why we want to limit stroke on these devices.
You don't want the actuator to break it.
So related to that, not to break the device itself, but because of fatigue. So if I apply, if my actuator can give me 5% strain at 200 MPa or something like that, maybe I want to use it at 100 MPa and get only 3% strain. That way my fatigue, hopefully we don't have any fatigue experts over here. If I go into my life and my strain, if I operate at maximum strain, Emax here, maximum strain I can get, maybe my life will be over here. Okay, that's my maximum strain. But if I operate half of that, I might just go over here. And my life is going to be a lot more extended. In fact, you know how these curves go. You go in there, you get some endurance limit at the end. Endurance limit does not exist in shape memory alloys. That's a debatable thing. I think it doesn't exist. But you can see how your life will increase. This is common to all metals as I decrease my stroke. So I don't want my actuator to be working so hard to get the full stroke, meaning, you know, I can use it at 100 MPa and go like halfway and then come back and go this way and so on and so forth. I don't want to go all the way under the max stress condition. And that's one of the reasons why you want to limit your stroke. In this example, so happens that we have a stop, so your device doesn't keep pushing against something else like you mentioned, and it gives you just the desired amount of stroke. Now, some people, some applications, some devices require a spring force. Now this becomes complicated because a spring, when you pull it, it puts the load. When you let it go, it removes the load. So my spring, my load line is not constant. As I heat up, my load increases. Okay, see my load is going up as I get the stroke out of it, and then decreases accordingly. So there could be a combination or any other sort of form, and I have seen some crazy different load lines that go in there. But realize what I did, anything that I do is in this box, right? Nothing is out here. That is outside of my range. And if you don't know where this range is, if you don't do your characterization, you know, spend a few minutes or hours doing this test, collect this data, create this relationship, gives me my box, and I can play in this box all day long. This is what I live for my actuator, and I can create any fancy load line I want. All right, so that's very important in the world of shape memory alloys. This is just an example here to show you weights. I just edited here. Some time ago, we did a trait study between an actuator that can produce, 100,000 inch-pounds of torque. And here's an examples of how much it do, 2 models, couple of footprints and weights. And what we ended up doing, we traded that against an SMA actuator, a tube actuator, that you can see for the same 100 inch-pound torque and angle, because that's how much we want. You want an angle of 90 degrees. You want 100,000 pounds of torque. So we traded that, and we got somewhere in the size and this weight of the actuator. And this is what the values are showing. 20% the weight and 15% the size of the comparable hydraulic system. And why I'm bringing this here is when we do the straight studies, sometimes we tend to ignore a number of different things. We tend to ignore the fact that can you make such device? Do we have tubes that are 2 inch in diameter or 1 inch in diameter? No, we do, but 2 years ago we did not. Number two is an hydraulic actuator can actuate very fast, and it's not traded here. You know, here we assume we don't care about the actuation rate, so we can get this 20% of weight and 50% of the size. But regardless, I'm trying to show you the benefit, but I wanted to also show you things that can hunt you later if you use the shape memory alloys. Actuation rate, weight, size, life, all of those things need to be addressed up front, not later. That's the reason why I wanted to put this one in here, but also to demonstrate that these SMA actuators can be really lightweight. To design SMA, I just put a couple slides here for you, and I referenced this paper here that gives you a lot more details. So you have to trade really all kind of things, the requirements, the cost, and the availability of the materials. I think we talked about that for a little bit. This chart here, again, from this work that we've done, you can do the design. You can also do some modeling. And for those of you that are modelers, I can point you to the right direction if you want to do some finite elements or some constitutive models. And characterization, which is important. You need all this need to come together to make it work. A couple of different things. I'm just going to rush through this because this is really just for your information only. Not necessarily for me to go through it, but you can see here you have different aspects of the design that we talked about, how to control it, how to get the alloy, what kind of process you're going to do to it, how you're going to train it. The model, it can be a first order model, something that I will show you today, or it could be as complex as you want it to be, find an element for all the bells and whistles. But also you need to do calibration for the model by doing the characterization that I showed you also. So you need that data. And this is how you get that characterization, following some standards or doing some kind of experimentation. And this can happen at the material level, but also at the subsystem level when the component is assembled and you want to test it and see how it performs. So that's multiple levels there to keep an eye on. So let me go to tools. Now I'm going to switch to a MATLAB little code, and I'm going to be running things and explaining a few things. So you want to design with a wire. You have an actuator, small actuator. You want to be able to pull a pin or open a gate or do whatever you need to do. And you need to size it right. You need to figure out how to do that using basic tools. This is not some finite element analysis. We have those, but this is not the purpose for that in this course. So here's a tool that we developed for predicting loads and strokes and an approximation of the life, how many cycles this thing will go under a specific load. Okay, so first here's a model, okay, an SMA wire of such length and a diameter, and is attached to a bias load. This is not two-way, this is one-way wire, and is attached to the bias spring to return it back to the cold state. I think we talked about how to obtain the characterization. You go between the hot state and the cold state, you know, you get this point and that point, and so on and so forth at different stresses. You know, this is pulled at room temperature, this is pulled at high temperature, and you get the difference between the stroke, and this is your design box. So you need this information in order for you to use this wire tool. Different description, and I'm going to jump straight to it and show you. So let me. This thing is not advancing. Okay, here it is. So let me get out of here. Can I go to this tool here? And I'm going to try to do it on the fly. And if you have any questions, stop me. And this tool can be made available to you to play with. So the first thing this tool comes up, it comes with some numbers to get you started. And the wire parameters, like I showed there, there's a wire length, how long this wire is. And that depends on how big is this actuator that you have. diameter of the wire. You know, depending, you can size it based, excuse me, based on the force that you're trying to accomplish. You can bundle, not necessarily bundle them like a cable, but you can have multiple wires. And then there's if there's multiple wires, because there's some contact in others, we have a heat transfer coupling value. And then this wire start at room temperature and you're heating it with some current. Right now I have these turned off. Okay. So the first thing we do is you're going to give it a characterization. You know your design box, and I'm going to load those curves. So now you know where we got these from, I hope. This line and that line. And basically, that was gotten from, this is MATLAB here. Can you, I'm assuming you can see my tool here in MATLAB? You can confirm?
Yes.
Yes, okay, wonderful. Yep. Okay, so this line's here, and they were, you know, done by you know, when I have my curve here, you know, I get this point and I get that point, and I plot it here and here, and then I go higher stress. I get this point, and I plot it here and here, and I create this box. So inside this box is what I live. And then I have this yellow line. This yellow line is my stop. Sometimes I don't need to actuate the full stroke, but I just need to limit it. Okay. Now I need to give it some external applied stuff here. Cold stop, where do you want this cold stop to be? I want it at 5. You can do it at 3 or whatever. Spring constant, like the model I showed you, a wire, you know, a spring attached to a wire. This has a spring constant that you can, you know from any spring, measure it or just buy the spring. You give it here, okay? Cold stop position, and you target stroke. I want this actuator to give me 2 millimeters or 5 or 20 or whatever that is. And then you simply, once you input these variables, it does some intermediate calculations and spits out this little box. This box gives you the stroke. Here is your spring constant. You see it here, like I showed, because that spring is not constant force, right? It changes from martensite to austenite. Your target stroke is 2 millimeters or so you don't have to go all the way from here to here. And you have a cold stop. That cold stop, you can change it to anywhere you want, really, and recalc everything, and it's going to move that cold stop over here. So it gives you intersection at cold. This is how much stroke I need to go out, and you need to move this cold stop accordingly. But this one is a very quick way. By the way, what we're solving here, you know, strain is L minus L naught divided by L naught, and the stress is the force divided by the area. Your very simple principles used here. And that's what this solution gives you. It gives you the maximum stress that is applied. You can see that you are at 233 MPa if you use the spring rate. It gives you your strokes, but also gives you a prediction down here. This is using the simplest fatigue model that we could find out there, and it probably gives you an estimation. I'm not saying it is the correct one because we don't even know how the SMA fatigue models work. But it gives you a first order approximation. It tells you this one is going to last 255,000 cycles, and this diameter, and this load, and this stroke, and this stop. So this tool really a very quick way for you to change its numbers quickly and look how much stroke you want to get and size up what the stress is going to look like and what the life is going to look like. Any question on this simple tool here? Okay, and the way we have it built is you can load your curve, or you can make your own little experiments. We have preloaded curves already for a wire off the shelf, but you can really measure your own and just replace the file where this one reads from, and you can study your own material and do the same trick. So any questions on here? Okay, good. So let me go to the next tool. So this is the simplest, in my opinion, form. You just do the wire and you design it. So the next one is, we're going to start getting more complicated here, is a spring. Why we want to use a spring? Springs are used because they can give you a large displacements compared to wire, but the force gets reduced quite a bit. So here we have a tool that does some prediction. You give it some SMA properties like elastic moduli, shear moduli, Poisson's ratio, and density. You give it some geometry like the wire diameter, the coil diameter, the length that you're working with, number of coils. It does some intermediate calculations, and then it calculates your stiffness at high temperature in the austenite and stiffness at the lowest temperature, and it gives you this box in between them where you can design your actuator. Now you can put some bias or whatever you want to do. So that's how this one works. And that's basically what it describes. If you never worked with springs before, depending how they were machined, there is a factor that you use to account for the end conditions. That's what this EC stands for. And then some basic geometry here, pitch and wire diameters and so on and so forth. So let me go to that tool now. Okay, so here's that particular tool here. And again, because we want people to start from somewhere, we give the properties of nickel titanium. We just put some basic wire diameters and coils and stuff like that, something that you can get off the shelf. And then if you take in these values, you calculate these values and you get some plots. So here, calculation of like spring index and so on, things that you need to design with. And then it gives you this plot here. This is the most important one here, is the applied force as a function of deflection. And really you see three lines here, what we call the reduced form, the modified form, and the full form. And what's really is, it's just the way the springs are calculated. So if you look at stresses in a spring, I'm just going to move this over here. If you look at the stress on a spring, so what we're using is the shear stress is equal to some force that you apply to it, right? Times the mean coil diameter. There's some factor that goes in there and divided by pi dq, something of that sort. So the shear stress is the highest stress in a spring, helical spring. So now this basic form here takes multiple variations. This is the simplest form, but if you want to account for some geometry correction, you have to multiply by a factor known as Wall's factor. If you need to account for large helix angles, imagine you stretch this spring very, very far. Well, that's what we call the full form after Anker and Goodyear back in the days in the 1920s. They use a much more modified factor that accounts for the helix angle, basically. So this is the function that it's solving here. And as far as displacement, it's just a relationship with the inverse to the spring stiffness. Again, times 8 times force times d cubed. And here you account for the number of active coils, and you divide it by a shear modulus. That's why we give you the shear modulus times this wire diameter to the fourth. So this is your equations for the springs that we're solving here with some factor here. There's a factor here for modified or full form or reduced form. That's what this spring tool is giving you. We have seen people use springs that stretch to almost a wire. So if you use your reduced form, it's not going to capture anything. So if your displacement is large, I recommend using the full form. In this case, it's very close. The one in the bottom here is the estimated of the stress and the effective stress. Basically, square root of these three summed up is the effective stress. And why is that important? You want to be able to know what is the effective stress as you apply load and stay below some critical temperature. You know, for example, in binary nickel titanium, if you go past 200 MPa, you're going to be in trouble. The material has seen a lot of stress. If you're working with nickel titanium hafnium and you go past 200 MPa, it's not a problem. It can handle much higher stress. These are just examples that you need to be aware of. So this is what the tool gives you, and now you have the stiffer side. So the material changes stiffness, right? When I go to higher temperature, see this? The austenite modulus is 70. When I go to lower temperature, the martensite modulus is 40. So the stiffness is changing. Okay, as the stiffness changing, if I have a line here in between them, like I showed you, a load line. So when I'm hot, the SMA takes over. When I'm cold, the SMA loses. So a lot of applications out there, people use an SMA spring in line. So this will be an SMA in line with another spring. Okay. And the way it goes, the stiffness of austenite is greater than the stiffness of the bias load. Okay, and here will be the martensite. So when I'm hot, when the SMA is hot, I pull one direction. When the SMA is cold, I'm being pulled the other direction. So this mechanism called antagonistic. You can use it to open valves or do whatever you need to do with it. So this mechanism comes up very handy when designing such things in a linear fashion. And this tool here tells you what those loads are as a function of geometry and properties. Any questions? Okay. So let me go to my other favorite tool, which is the torque tube. Where are we? Here. So now we have another tool if you want to design a torsional actuator using a tube that twists. So this tool here takes into account a lot more baggage than the other ones. You can see here you have some material property, geometries, and then material properties. And here are those things again, that CA and CM, which is the stress sensitivity, those Clapeyron slopes. When you apply a load, the temperatures shift. Those become important, and you have to account for them in these models. So you work with that. How do you do characterization and torque? The same way you did it in axial, uniaxial mode. You apply a torque, you measure your actuation strengths at different stresses, you create your bounding box, and you feed that into this low 1D type model. Oh boy, my computer started to act up again. Here it is. And these are just some graphical representation of what the actual data looks like. We actually tested to validate this model, this 1D model. Here is the experiment data, and here is the tool prediction. Oops. Here's the tool prediction on heating and cooling. So I'm in slide 79. Hopefully there's no lag between me and what you see. I'm in slide 79 of your package and showing prediction. The other thing that we look at is what kind of ratio of diameters you use. You know, do you go higher in diameter, or do you go thinner and thinner wall thickness? And you can see that the curves matters. If you go thinner and thinner in diameter, your torque is decreased. If you go higher in diameter, your displacement will be decreased. So what are we solving here? I heard something. Okay, maybe not. Okay, so what we're solving for here, you know, you have your shear stress is equal to a torque applied times the radius, typically the outer radius, divided by J, the second polar moment of inertia. And this one has a relationship to the inner outer diameter if it's a tube, or just a diameter if it's a solid. So as you apply a torque, higher torque, you get higher stresses. But now if you hollow this up, this is going to be bigger, and you decrease your stresses if it's a hollow tube, not a solid tube. And as far as what is it, the twist or display or strains here, what we're solving for, we take a strain of a material, and I'll show you that the amount of twist that you get out of it times the radius divided by the length, the effective length of this tube. So if my length increases, okay, my strain is going to increase. If I increase the radius, my strain is going to decrease, and so on and so forth. It's a combination of these two values that you got in there. Okay, So let me show you that tool here, which hopefully can clarify some of these things.
Question for you.
Yeah.
Does that have to do with the twinning of the base material?
Twinning happens in all forms of actuation, whether it's uniaxial or whether it's torsional. So the twinning go ahead.
So it seems like what you presented, you know, the more material there is for deformation, the more angular twist you're going to get out of it.
If ignore the solid line here, at some stress here, changing the wall thickness at some nominal stress up to 300 MPa, you can see this bundled line here. They are pretty much equal. Okay, so again, this is angle of twist as a function of shear stress. So the shear stress has been normalized. The torques applied are different according to that equation. So the torque applied here is much higher than the torque applied here, but the effective stress is the same when normalized. So either I have thick wall or thin wall, I have the same kind of displacement over here. Okay, so this relationship not necessarily correct, and there's this departure from the solid, which is solid have issues with gradients. So the heat doesn't go to the center. Let me try to share my screen this way so I can sketch on it. So there's some profile that looks like this, okay, in conventional metals. The stress in the metal is 0. As you go out to the outer shell, the stress is maximal. In the SMA, frankly, we don't even know what it looks like. Maybe like this, or I have no clue what that stress distribution looks like. But if I have a solid of this form or that form, you can see here they are all the same. Okay, in the normalized fashion. In the normalized, if you plot it as load, obviously it's going to be different. According to the shear stress is the load times the radius divided by J. Okay. So that's
okay, and then one last related question to the tube, the torsional tube. So
yes.
To create a torsional tube, you have to form your tube and then set it in a twist fashion at 500 C and set it, and then you've got your torsional tube.
Yes, so we cut the tubes, we gun drill them, we spline them or hex them on the edge, and then we don't shape set them, but we train them. Okay, so that's the only two ways to get the form is by shape setting and jigs, or by training them to remember that shape. And the training is apply a twist to it and do a bunch of other things. Suddenly the tube doesn't know to extend or to bend and only knows how to twist. So that's what that training does to it, really.
Okay, so you're implying something other than a heat set, something more like a peening or a work hardening for training?
The training that I'm referring to, basically, you have to take a tube, put it in a rig, and apply a torsional load to it, and then heat it and cool it a bunch of time. By doing that, you are aligning those twins or those martensites that go back and forth. You are almost telling them what to do when you heat and cool. And what training implies, you create a path. So imagine when you create a material from scratch, the material can extend, can twist, can bend, do all these things, right? And that's governed by how those martensite twins move. But now if I take this tube and I apply this thermomechanical twist and twist, twist and twist, you create almost like a highway of where the martensite should go. Now the martensite follows the lowest energy state. It looks left and right. I'm just going to go this path. That's the training path. And that path is carved, and if I can use that word, is carved into the metal by a number of different defects, a number of different retained structure that allow it to only remember one way, one path, one highway to go through, and it forgot the rest of them. That's what the training implies, and that's how we do it.
Got it. Thank you.
You're welcome. So now if I go to my tube model here very quickly. I'm gonna run this tube thing. So this simple calculations here that we have, that we refer to it quite a bit actually. So now let's say you know nothing about tubes and you come in and you need to size a tube. You know what roughly the torques you have, and you need to wall thickness and how much displacement you're going to get. So we basically boil those equations to this. So here I'm plotting torque as a function of wall thickness, and I'm plotting them as a function, and the colors refer to different stress levels. Depending on the material that you have, maybe you don't want to exceed 200 MPa. In some high strength materials, you can go as high as 500 MPa. So this gives you, if I go up 0.2 thickness on this 0.75 OD tube, and I apply, I want to stay at 200 MPa blue, my torque limit is going to be 2000, or you can do the opposite. If I'm looking for a 2000 torque input, I can choose my wall thickness for my material. Now you choose your wall thickness, you go to your length. Okay. Now you know you want an angle of twist outputs, and these are based on different strain levels. The bottom one is based on two-way strain only, two-way shape memory effect. The top one is the maximum on one-way plus bias shape memory effect. So if I only have two-way, and I need a length, I need some actuation of 50 degrees, or let's say 60 degrees, I can have a tube that is 15 inches long. Okay, and so you get my point here. If you have it biased somehow, and you're looking for 100 degrees of twist, you can also get 15. So you can have this going from two-way to bias one-way, and you have this design freedom to allow you to play with it a little bit. We use these tools for the big tubes that we use, the 30-inch long, and we also use them for those little ones that we use for the vortex generators that are like 1/8 of an inch in diameter and probably 2 inches, 3 inches long. So the same formulas apply. And so that's as far as sizing of wall thickness and sizing of length. To get the response out of them, we use this tool. That I showed you on that PowerPoint slide. I heard a ding, so hopefully it works. So here, that tool, SMA parameters here as far as modulus and some values. Here are those slopes that I was referring to. Here there's set constant, some tube geometry, depending on what you're working with, thickness, radius, length, and so on. And we also allow it to input some power. Sometimes we use induction, sometimes you will use cartridge heaters, but that boils down to some power in watts. Okay, and here are some thermal properties as far as emissivity and specific heats. And then once you run this model here, it does its prediction. It gives you a prediction based on this one. By the way, we gave it that calibration curves, right? Maximum strains, minimum strains, those, what I call it, those actuation plot, right? So you know that you did your experiments, you know what the minimum strain is based on two-way, your maximum strain based on full bias, you know what your stress sensitivities are, and then you can play with a bunch of geometries and plot out your strains, rotation, and stresses. So that gives you a full scope of what the three main parameters you're looking for and what temperatures they are actuating. This happens to be a 400 Kelvin alloy, like a 200C alloy or something like that. But without going to finite elements, without going to some very advanced model, you can just play with these tools, size your tube, get it roughly where you want it, and then perhaps just with a few experiments, you can hone into what you need to design with. So that's what we use the tube for, designing of torsional actuators. Torsional actuators, we use them for those vortex generators, for example, and for a number of different things. Any questions there? All right. Finally, the last tool before we end is this one right here. This one might take a while to run, but I'll describe it. So I described using tools to build an actuator, but this tool that I'm going to go with right now is a tool that allows you to pick the right material. We call it the shape memory alloy or shape memory materials database. Shape memory materials database. So basically from all those alloys that were created since the 1950s, they are, you can spend a decade trying to find the right alloy, but we created this database so anyone can go in there and start looking at what are the important parameters here. You're looking for strain or temperature, or maybe your thing is you gotta watch out for cost and things of that nature. So let me go to an example here and broadcast it here. So let's say you have, this is a case study here. Let's say you need a material with an austenite finish temperature of 250 and a martensite finish 150. Basically, your design box is between 250 and 150. Okay, that's somewhat in there. Okay, and then when you plot, you go to this database that I'm going to show you in a minute. You get a bunch of different alloys, tons of different alloys, just in the nickel titanium family. Well, you want to down select. Okay, let's down select. You need an actuation between 4 and 6. Okay, here's that 150, here's that 250. 250 austenite finish, 150 martensite finish. And then you have some versions of that, so the data has been dwindling down to a subset. And then you really cannot afford precious metals. Okay, so all these platinums and palladiums and golds are gone, and now you slowly hone into an alloy that can actually work for you. Okay, in here. So that's the whole gist of this database here. So let's say you're working with nickel titanium and you want to look at what properties you're interested on. You're interested in austenite finish and martensite finish, but then you want to look at what elements can I add to it, for example, to get my design variable. And this is happening in a few clicks here, like you see. And you can put all these different elements, look at ruthenium, look at scandium, at zirconium, at tantalum, whatever you want to look at. And within a few clicks here, you can find an alloy that suits your application based on the properties that you're looking for. You can apply a bunch of filters. You can compare, for example, hafnium and zirconium can give you the same properties, but zirconium is cheaper than hafnium. So if you can get the same property, same temperatures using zirconium, you'll go with it. And you have to also weigh in the other options like cost and dimensional stability and training and so on. So this tool here, we use it for, or we're still really developing it. It's not fully done yet. But the idea here, it takes data from the 1950s, all published papers since the 1950s on shape memory alloys, puts it in one place, and within a few clicks, it allows you to go through millions of data points literally and filter based on what you want and apply whatever to do and select an alloy. And once you find that alloy, let me see if I can do it here. Once you find that alloy, it gives you its information. It gives you its composition, a process, how it was melted, and it also gives you some information on who published that work. So maybe you can go back and read that paper, or you can call that guy and buy it from him, or whatever you need to do. So that's what that other useful tool in the world of shape memory alloy that we are trying to come up with is materializing to be a very useful one. So with that, the rest of this reel, I wanted to leave some time for some final questions. I know we end at 4 o'clock in 10 minutes. The rest of your packet, I'll go through it very quickly. It's just a number of different examples. I covered this one, the drone that we flew with moving the wingtips up and down. Boeing did an experiment moving the flap here up and down using tubes. Langley did an experiment with the chevrons on the engines. You can see here another fan nozzles with Boeing using this kind of, you've seen the rock splitter, the vortex generators. CubeSats can really benefit from these materials because they are SMAs are very tiny. You can package them in CubeSats, very small places, for retention and release mechanisms to release antennas, maybe solar panels, maybe booms, orientation devices. This is another application with Johnson, our friends at Johnson, and collaboration with Texas A&M and Paragon, is space radiators. So this SMAs close and open this radiator to expose more or less of the skin, so you can change your heat transfer coefficient and whatnot. Emissivity changes, and you change your radiator turn down ratios, really. So SMAs are attached. You can close it or open it depending on what the temperatures are doing. And this is the work being done with Johnson. Showed you this, but again, this is just examples. I would like, if possible, let me just finish them up here. Here, this is, I'm in slide 106. This is important information that you can go and find some standards to learn from. For the biomedical, they're listed on the left. For the actuation, they are listed on the right, only 2 for now. And that's what they are, really. I also listed a number of different vendors that you can go right now and buy some shape memory material or buy some shape memory device already packaged and built as a motor. So this could be handy if you want to experiment with something in your lab or try something in your devices. And of course, if you don't find them commercially, give me a call. There's a number of different resources out there, people that go to conferences or people that used to go to conferences. I don't know how that's going to look like now. There's some prime conferences and groups that look at shape memory alloy from the fundamentals to the final device manufacturing. But this is, again, just stuff that references where you can use and learn from.